All right, you ready? Oh my gosh, I drank a big old coffee and I'm still. Do I have one more? Or can I not count? 12. There we go. We got 12 now. Okay. Yep, it's C. Woohoo! Are you excited? Mm-hmm. All right, how about this one? Did you get one? Yeah. Yep, it's B. The nitronium ion is the electrophile. Remember, we're doing electrophilic aromatic substitution. So every reaction has an electrophile, and that's what the benzene goes for. Okay, this reaction uses SO3 and sulfuric acid. It's called sulfonation. What I did. Okay, notice that your product is not just an SO3 on the benzene ring. It's an SO3H. Okay. Sulfur trioxide is your electrophile. Oh, hang on. Pen. Come on. So picky. Oh, should have written B. Okay, so that's your electrophile, your E+. Okay, here is the resonance form for SO3. Notice that it is still electrically neutral. You have a plus and a minus within the compound. Okay, so where is the electrophilic site in the sulfur trioxide? In other words, where are we going to go? Oops. Apparently not anywhere. Okay, so we're going to go to the S. Okay. Then what will happen is you can go out to the L. Now remember, sulfur does break the octet rule, so you can even write your sulfur trioxide like that, with 12 electrons around the sulfur. Blows them up. Okay, so let's look at the whole thing now. Let me use a pen, maybe that'll go a little better. Okay, I always tend to use this double bond, so I'll put the H's on that one so you keep track of them. There's H's, remember, on every one of those carbons. Okay, and we're going to add S. Okay, so here is our Benzene attacking our electrophile. Okay, so what are we going to have now? We're going to have our benzene ring with 2 double bonds that didn't get touched. Remember, these 2 hydrogens are still here. Okay, one of these carbons, and it doesn't matter, again, which one you pick, is going to be bonded to the sulfur, and the O is going to have a negative charge on it. What else am I missing in that picture? What else do we need? Just like the other one. Yes, a positive up here on that carbon. Okay. Okay, now, you know where we're going. What do we have to do to get there? We have to get aromaticity back in our ring. So to do that, we have to lose the, which one? Yes, this one. Not that one, this one. Okay, what else do we have to do? We have to do 2 things. We have to add a hydrogen to the O minus. Okay, it really doesn't matter which one you do first or what order. Okay, so since we've been doing the this one, we'll do this one first. So here's my base. You could also use HSO4 minus, but this is probably more likely. It's going to pull off the H, and these electrons are going to go there. And what do I have now? Works better if I don't pick it up. Sure. I am going to draw that H in, and then over here I have this part. Okay, and now I have my double bond. I got my aromaticity back. Okay, what happened to the water? It became, what is that called? What's that called? Hydronium ion. Okay, just checking on you. Okay, let me make that plus a plus. Okay, so now what happens to that molecule? Because we're not done yet. We have to protonate that O minus. And it doesn't matter which of those hydrogens on hydronium you pick. There's also hydronium ion just running around in there because we have sulfuric acid. Sulfuric acid is dissolved in water. That makes hydronium. So just use a hydronium ion to protonate. You do not have to draw out the structure of sulfuric acid. It's okay. Okay. Are you with me? Okay. Notice how it's the same as the other one. Okay. Now on this one, you also are going to have resonance forms for your, what is this called? Benzenonium ion. Okay. So make sure that you know how to draw those. So instead of worrying about the SO3, I'm just going to write SO3 minus. Here's your plus. Okay, so how do you draw those resonance forms? We go from the double bond up there. Okay. Use your resonance arrows. Okay, so I'm going to draw what didn't change. We didn't change that double bond over here on the right. We didn't touch the SO3 minus. This hydrogen is still there, okay? And if you're having a hard time, put all of the hydrogens in so that you don't make a 5-bonded carbon by accident. We would never do that, would we? Okay. All right, so now when I do this up here, what do I have? A double bond, and this carbon has now become positive. Okay, is there another one?
Yeah.
Sure, bless you. We're going to move the other one. Oops, I need black. All right, so this time I'm going to do the same thing. I'm going to draw what didn't change. Okay, so we have, let's see, we have a double bond here. Okay, then the rest is what changed. I'll try to put in some hydrogens. I can't promise this pen is going to go where I'm putting it. Kind of irritating. All right, so what do we have here now? And then this carbon has now become positive. And if you need to see a better picture, look in your book. That one looks pretty good. I'm not going to lie. Okay. Okay, Friedel-Crafts Acylation. Okay, so what are we going to put on the ring? We're going to put not just the R.
Yeah, everything chloride, right?
Right, yeah, all of this is going to get put on the benzene ring in place of a hydrogen. I have one hydrogen drawn in there. Okay. Okay. Okay, here's your electrophile. That is referred to as an acylium ion. Okay, you only get that formed if you have aluminum trichloride in there. Okay, so you have aluminum trichloride in there. All right, so hang on, I'm gonna. Okay, what happens is the aluminum trichloride hooks onto the chlorine and helps to pull it off. Okay, that is then stabilized by the lone pairs on the oxygen, which is how you get the acylium ion. Okay, I think I have a picture of that on the next slide. If I don't, I'll draw it all out. Okay, I want though you to notice that there's a 1E and a 2. The 2E is just, you typically just add the water to help neutralize any excess AlCl3. There isn't really a whole lot more to it than that. That's what it's for. Okay, so here is making the electrophile. I was pretty sure I had this. Let me get another go. All right, so these electron pairs go to the aluminum. Okay, when they do that, you get these electrons leave. So you get R, C double bond O plus, like that. That's a plus. I'll try circling it. Grr. Okay, then the resonance form is these electrons coming down to stabilize the plus. Because the oxygen being bigger, it can handle the plus charge better. Okay, there we go. We got it. There's your acylium ion. ACYL IUM ion. Okay, so now we're going to take our benzene ring and we're going to react it with that acylium ion. Where does it go?
To the part.
Yes, it goes to the carbon. It does not go to the O, even though the O is plus, because you won't alleviate the plus charge unless you go to the C. So look what happens when you go here. Now what can we do? Follow through. And now we've alleviated the plus charge. If you go to the O, try to do it, you'll see the O will still have 3 bonds. It will still be positive. Okay. All right, so here is our benzene ring. Okay, and now we have a bond from the benzene ring to that carbon. So here's our new bond. Okay, what else is attached to this carbon still? The hydrogen. Okay, and there's a hydrogen on this one too. Okay, now what do we need?
Base.
Whoa. On our structure first. Then we're going to do
The
that.
positive about that.
Yeah.
hydrogen on top.
Okay, don't forget your, I have some of you who like to not put any charges on it. Okay, I'm trying to get you to put your charges in. They matter. Charges matter. Okay, now what happened up here when we did this thing? What did we make? AlCl4-. Okay, well, the AlCl4-, and so that's aluminum with 4 chlorines and a negative charge, which is bizarre to begin with. Okay, it does not want to stay that way. So it removes that proton and falls apart. That's how you get AlCl3 regenerated and HCl. AlCl3 is your Lewis acid catalyst. Okay, so it's a catalyst, so it has to be regenerated. How do you feel about that? It's kind of weird. But I want you to see how similar every single mechanism is. The only thing that's going to change is how you make those electrophiles. But the basic mechanism is the benzene goes to the electrophile, you lose aromaticity, you get it back. By losing that proton. Always those 2 steps. This one and this one. Now the SO3 one had the extra step of the protonation. Okay, that's only one. All right, here is Friedel-Crafts Alkylation. This is the one you did in lab, okay? So you have your T-butyl chloride and AlCl3. And what are we going to put on the benzene ring? Yeah, a T-butyl group, right? Doesn't matter which carbon you pick. I just picked that one so I didn't have to redraw my thing every time. I could copy it. Okay, you must have a Lewis acid catalyst again. Okay, here is your electrophile. It's a carbocation. Wants to be the most stable carbocation. Remember those little deals from last semester? Okay, we've even reviewed them already some this semester. Okay, so the next slide, we're going to do the mechanism. Okay, are you still writing? All right, I'll let you write. Okay. Oh, I have this next. Sorry, I forgot this was. Okay, so what do you get from this? Okay, how'd we do? Yeah, good job. Don't fall for those other answers, right? Okay, it's just that. Okay, What would it be if you didn't have the Al-Sil3 there?
It would add to chlorine.
It would be no reaction.
Sorry.
Yeah, because being aromatic is so stable that you have to make the electrophile in order for it to do the reaction. Okay, not that I would trick you like that, but other people might trick you like that. All right, so here is RCl. This is our alkyl halide, and we're going to react it with aluminum trichloride. Pairs, my lone pairs, maybe. Okay, so when we do that, the aluminum is going to go for the chlorines, lone pairs, and this bond is going to break. So you're going to get a pen that doesn't work good. Okay, so that's your carbocation, and the AlCl4 minus is your counter ion, which is kind of weird, I think. Okay, so now we're going to add our carbocation to our benzene. Okay, remember how you draw the arrow, the electron movement, electron movement. Don't draw the R plus going there. It's going there, but that's not what the arrow is. Okay, so now we got, here's our benzene. I'm going to draw what didn't change. Okay, now what do I have? I have a bond to the R. Okay, what else do I have? A carbocation up here. Okay, and what else do I have? I have that, right? My AlCl4 minus. Okay, so to get to product, what do we got to do? We got to lose a hydrogen. Which hydrogen are we going to lose?
One by the R group.
The one by the R. Do you see that if you lose this one and you go down, that you're making a 5-bonded carbon? Okay. I'm only mentioning that because of how many hundreds of times I've seen it. Okay. So you got to figure out which hydrogen is the one to remove. The one that the R group is replacing, the one that the nitro is replacing, the one that the chlorine is replacing. That's the one you have to take off. Okay. All right. So now we're going to remove this proton, and these electrons are going to go there. Okay. And so we're going to end up with our R group being on the benzene ring. Plus HCl and AlCl3. Okay? Are you seeing how they're like the same thing? Oh. Okay. That's actually what most students like about electrophilic. It's very repetitive. Yeah. Okay, so predict the product. Predict the product. Okay, you have a little clue there. Oh my God. Is it not in there?
Yeah.
It's just.
So it's going that
I
big long.
skipped that one? Oh, I think I switched the order. Because I think we're going to do that
Where
one
the
too.
hydrogen is, that big long thing is going to be attached to it.
Okay. So if you have What kind of carbocation is that? That's what? Primary. Okay. Isn't that the least stable? Okay, so how can we make it more stable? Okay, and who's moving? Methyl or hydrogen? The hydrogen's moving. If the methyl moves, it just becomes secondary. The hydrogen moves, it becomes tertiary. This is how they know the carbocations are formed, because anyway. Okay, so don't forget that. That's like always an issue. Anytime you have a carbocation, you can have a rearrangement. Okay, so what do you think the major product is for this reaction? Did I open it? Yeah, I did. It's on the square. This little dill isn't going away. Yeah, see if that makes it go away. Yeah. I'll do it here too. Okay. All right, we're all up there. You ready? Well, that about covers it, doesn't it? Okay, so what is the first carbocation that you're going to get off of here? Hang on, let me get a CH3, CH2, CH2, CH2 plus, right? Then you're going to have this. That's your counterine. Okay? Do you get some butylbenzene? Yeah, you do, but that ain't your major product. Because what kind of carbocation is that? Primary. Can we make it more stable? Sure. Okay. We're going to move a hydrogen over. And what kind of carbocation do I get now? Secondary. Okay, now your benzene is going to attack that carbocation. Things that occur within a molecule are faster than things that occur between molecules. Okay, can you tell me the name of that? Was that part of the problem? What? It's sec-butyl.
I named it wrong.
Oh, well, that's all right. Hopefully on the test you'll just have to draw structures. Okay. Okay, you got to know these groups. Like, they come up all the time. Okay. Notice that it's on the second carbon in the chain. What is isobutylbenzene? CH2, CH, CH3, 2. That's isobutylbenzene. See, butylbenzene was on the left. Okay, help you remember. Okay, what do you get from that one? No names. I thought it was 13. Am I right? What was 12 before Greenwich came? Yeah, right. Okay. Good deal. Okay, now what do you think you get from these? You figured them out now, knowing what you know. Come up with an answer? Not a clicker question, so feel free to try. Okay, did you get that? How do you get that? Okay, so what happens when you take this and react it with HF? What do you think will happen? You will get a carbocation, right? Doesn't matter which side the H goes to, you actually get the same one, right? So you would get and this carbon is plus. Okay, so we made a carbocation just like we used in the last one, only we made it a different way. Okay, so this will work real well. Now, it wouldn't work real well with HCl or HBr or HI, because what else do you get off of this? You get a halide ion, right? F minus, okay? If you had chlorine, bromine, or iodine, they would add to the carbocation. But fluoride is a crappy nucleophile. So because of that, this one works. Now, kicker is you have to work with this. It's not fun. HF is hard. Like it'll eat up Teflon. Yeah. I never worked. And I'm not unhappy about that in any way. All right, now we have an alcohol and we have sulfuric acid. What do you think is going to happen? The alcohol is going to get protonated, and then it's going to leave, right, and form water. And what are we going to what's going to happen to this organic piece? We're going to get CH3, CH, CH3. Okay, so what's our benzene going to do? It's going to add to that carbocation. Okay, so did you get isopropyl benzene, aka cumene? Remember that? Mm-hmm. You're glad I didn't put that on one and just keep the name. Okay, cumine's a weird one. It gets used for special stuff though. Okay? That, you getting it? Okay, if you take this one, this is the one I showed you already, and you run it at 0 degrees, you get 35% of the T-butyl. What's the major product? The one that's rearranged is the major product, right? Okay, so they upped it a little by running it cold to try to inhibit the carbocation rearrangement, but it doesn't work very well. What if this is the one that you want? what you have to do is make it. Okay, if you really want 1-phenylbutane, okay, what we do is we do it like this. Okay, so you remember this one? What did we put on our benzene ring? The carbonyl and the R group. Okay, so when you do this, it does not rearrange. Acylium ions do not rearrange. Carbocations do, acylium ions do not. Okay, but we're still not at this compound, are we? Okay, what's different between this one and this one? The carbonyl is a CH2 up there, right? Okay, so what happened is people came out with ways to go from here to here so that they didn't have to deal with that rearrangement. An extra step is better than dealing with a 35% yield. Okay, like if you're thinking, well, I could still just do that and then separate them. Y'all, it's really hard to separate. They're very similar in boiling point, and doing those fractional distillations is really speaking from. Okay, I told you about the really big one that I did that was supposed to separate the 2-degree difference in boiling points. And it had this little band inside that spun around to heat the column up. What ended up happening is I had only so much liquid to start with. Everything was in the column and nothing was coming out. So you're not supposed to go to dryness. It was awful. And I'd spend, well, you did it too fast. Oh, we'll do it again. And I spent like all day. And the column was so tall that I had to stand up on the bench in order to read the thermometer at the top. Like I literally had to stand up on the bench. Yeah. Not really a good thing to do. I guess I should have made them get me a ladder, but I don't know. Yeah. Anyway, it never worked. I ended up never doing it, getting that little thing to work. Okay, remember another way to write carbonyls is C with the O in parentheses. You will see that in your book and stuff, so just make sure you remember that. Okay, I tend to write them. I like to write them. Okay, so there are 2 types of ways to reduce carbonyls to CH2, and you get to do it in one step. Okay, they're called the Clemmenson and the Wolff-Kishner. Both reduce a carbonyl in an aldehyde or ketone to a methylene. Remember, a methylene is a CH2. Okay. Oops. This one is the Clemmenson. It uses zinc and mercury. And you notice they have that little parentheses. Have you heard of the word amalgam? Anybody in dentistry, they use amalgams to fill your teeth. Okay, your cavities. An amalgam is like 2 metals put together. Okay, typically amalgams are made with mercury. We don't put mercury in anybody's teeth, but they did used to. Oh, and they used to put gold in them too. Yeah, that's why people would rob graves to steal the gold teeth. Does that not blow your mind? Eek, it's an awful lot of work for a couple of gold teeth. Okay, this is called the Clemmenson. It's in acidic conditions. Both of these are going to do the same thing. Okay, but the difference is one's in acidic conditions and one's in basic conditions. This one uses NH2, NH2. Does anybody know what that's called? You heard of hydrazine? No? You don't ever pay attention to the space program? Hydrazine is one of the fuels they use on rockets. Hydrazine. That's where I thought you might have heard it. And I didn't know if they used it at all in germ camp, because you won't use it in the lab, but they might have used it for problems and stuff. Okay, notice that this one is in OH minus. Okay, both of them take a little heat. This one is called the Wolff-Kishner, and this one is called the Clemmenson. You'll run into those. People talk that way. Like you'll read an article and it'll say they use the Clemmenson reduction. Okay, that's the Clemmenson reduction. Okay, you can find out what it is usually somewhere in the article, but notice we got the same thing. So if you were trying to make that propyl benzene over there, okay, you would make this one first. So you would go, here's your benzene, okay, and you would add CH3, CH2, C double bond O, Cl, and AlCl3, and you would get that. It wouldn't rearrange. If you tried to do the one with the carbocation, propyl chloride, it would rearrange to the isopropyl. So that's why we do it this way. And then you could pick either one. Okay? Later on, it might matter. If you have something in your molecule that's sensitive to acid, then you would use the base. If you have something in your molecule that'll come apart with base, you would use the acid media. That's basically how it works. Okay? So you got that? Okay. So what would you get from this one? Okay, so if you look at this molecule, it's almost the same as the other one, except we have this weird cyclohexane ring and an OH. Okay, what would happen if you reduced it under acidic conditions? Any idea? Well, notice we reduced it at the top, but what happened to our alcohol? Right, because it reacted with HCl. So remember those old reactions? They come back to haunt y'all. Okay, so alcohol plus HCl gives RCl. Okay, so you have to, this is why you would use the basic conditions, because you don't have that problem, and the alcohol would still be. Now, if you're trying to do a twofer and get two things to happen at once on purpose, well, then it's tough. Most people aren't doing a twofer. Okay? All right. The best method to prepare pentylbenzene from benzene. Okay? Here are your steps. Remember that CO, that means carbonyl. Bless you. Okay. It might take you a minute to figure that. We're going to make pentylbenzene from benzene. Okay, these are the reagents. Four. Okay. I can give them one thing. You have to write it down. You might have to write them down. Think about each one and decide. All right, are we all up there? Y'all made a decision? Let's see how we did. Well, that about covers it. Okay, so how many carbons is there up here in that group that we're putting on? How many carbons are there?
5.
5. It's pentyl benzene. 2, 3, 4, 5. Okay, what's wrong with A? it'll rearrange. Okay, that's what's wrong with A. What's wrong with B? Well, you put a chlorine on. What does step 2 make it? A what? Grignard. Yeah. Okay, so you will have, so step 2 will give you this. Okay, what happens when you add this? 1, 2, there's 3 of those, C double bond O, CH3. What happens? This goes to the, yeah, and then we go. Okay, and what does the sulfuric acid do? Yeah, it protonates it. Okay, so does that give us this? It gives us a what? An alcohol, first of all. Okay, all right, so B's out. All right, let's look at C. So we're going to take our benzene and we're going to add CH3, CH2, 4, C double bond O, Cl, okay, and AlCl3. What does these two do? Takes off the chlorine and you make an acylium ion. I'm trying to say it a lot so that you learn it. Okay, so now our benzene, I'm going to put my double bonds in there. Our benzene is going to go to the, okay, and then we go out to the O. Okay, so what do I have now? I'm going to run out of room, aren't I, during all these? Okay. I'm going to have C double bond O. How many CH2s? 4. And then the CH3. And then I got an H and an H and a plus. Okay. And then we're going to deprotonate, make our benzene. Okay. And then what does this do? It reduces it down. What do you get at the end of C? pH for benzene. How many CH2s? 5 CH2s, right? Okay, is that what we want to make? We want 5 carbon. That's why it is D. Okay, remember that the carbonyl carbon is the very first carbon that's attached to the benzene. Okay? Okay, because I think most everybody puts C. All right, that carbon doesn't go away. Okay, now this is the end of the material for the test. What we do on Monday will be on the next test. Okay? So all we're going to have are the basic reactions from this. Adding one thing. I don't know. You'll just have to look for problems. Yeah. I honestly don't know what this is. It changes every year. So it's not unusual. It's just kind of like how it goes.